In the field of artificial intelligence, reinforcement learning has always been regarded as an important method for enhancing the reasoning capabilities of large language models. From AlphaGo to OpenAI's O-series models, reinforcement learning seems to consistently deliver significant progress. But a recent study challenges this perspective. Does reinforcement learning truly improve large language models' reasoning ability? Or might it actually constrain the model's potential? Today, we are going to explore the real impact of reinforcement learning training on the reasoning abilities of large language models. This research primarily comes from the team at Tsinghua University, who have drawn thought-provoking conclusions through extensive experiments. Researchers tested language models of different scales, including various models ranging from 7B to 70B parameters, on their performance in mathematical reasoning and programming tasks. They discovered an interesting phenomenon. While models trained with reinforcement learning performed better in a single attempt, pass at 1, in multiple attempts, pass at 256, the base models could achieve comparable or even higher accuracy. Here, we need to explain what pass at n is. When a model solves a problem, researchers will have the model generate n different answers. As long as one of the answers is correct, it is considered that the model successfully solved the problem. Pass at 1 means generating only one answer, while pass at 256 means generating 256 different answers. This is like a student taking an exam who can try different problem-solving methods multiple times. As long as they get it right once, it counts as a success. The researchers conducted detailed tests on the OmniMath dataset. Taking the Quintuo 0.57b model as an example, the base model could only solve 9.9% of the problems in a single attempt. But after reinforcement learning training called GRPO, the model was able to solve 26.1% of the problems in a single attempt. But the story is not that simple. When the researchers allowed the model 256 attempts, an interesting change occurred. The base model was able to solve 67.2% of the problems in 256 attempts, while the reinforcement learning trained model could only solve 66.3%. This finding is surprising because it shows that while reinforcement learning training improves single-attempt success rates, it may limit the model's overall exploration capability. To understand this phenomenon, the researchers analyzed the reasoning paths generated by the model. They recorded each step of the model's thought process while solving problems, then compared the reasoning paths generated by the base model and the reinforcement learning model. The researchers found that all problem-solving methods used by the reinforcement learning models were actually already present in the base model's knowledge base. It's like a student taking an exam. The base model knows multiple problem-solving methods, while reinforcement learning training simply makes it more inclined to choose those problem-solving paths that are easier to score points with. Let's use a specific math problem to illustrate. Suppose there is an algebraic problem. A base model might use different approaches in multiple attempts: direct substitution, factorization, or setting up a system of equations. On the other hand, a model trained with reinforcement learning, influenced by the reward mechanism, will tend to choose the most straightforward method that is easiest to receive rewards, such as direct substitution. Although this method is more likely to succeed in a single attempt, it may overlook other, more optimal problem-solving approaches. In programming tasks, this phenomenon is even more pronounced. Researchers found in the live code bench dataset, test set range 400-450, that the base model, Quen 7b Instruct 1b, could solve 23 programming problems, while the reinforcement learning trained model, Coder could only solve 19. By comparing the specific problems the two models could solve, researchers found that most problems solvable by the reinforcement learning model could also be solved by the base model. This further proves that reinforcement learning training may limit the model's exploration ability. Why does this happen? Researchers believe this is related to the objective function of reinforcement learning. Reinforcement learning focuses too much on short-term rewards, just like a student who only cares about exam scores while neglecting the real learning process. This training method makes the model conservative, only choosing paths that are easy to obtain rewards and not daring to try new, potentially more creative methods. This discovery has important implications for the field of AI. First, it reminds us not to overly rely on reinforcement learning training to improve the model's reasoning ability. Second, it shows that foundational models inherently possess the capability to solve these problems. They just need more opportunities for exploration. Is there a better way to improve the model's reasoning ability? Research has found that knowledge distillation may be a more promising direction. Unlike reinforcement learning, knowledge distillation can indeed introduce new knowledge into the model. This is because the working principle of knowledge distillation is to have a smaller model, student model, learn from a larger model, teacher model. The teacher model generates detailed reasoning processes, intermediate steps, and the student model learns by imitating these processes. Finally, let's return to the initial question. Can reinforcement learning truly enhance the reasoning capabilities of large language models? Research tells us that the answer may be more complex than we imagined. While reinforcement learning can indeed improve model performance on certain tasks, it may also limit the model's exploratory abilities and creativity. This reminds us that on the path of AI development, we need to maintain open and critical thinking, continuously exploring more effective training methods to truly enhance the model's reasoning capabilities.